So let's go ahead and solve an example. There is one of these there is a problem very similar to this in your homework, and I wanted to make sure that wasn't the first time you'd seen it. So the way we find the location of the latitude of a location L on the Earth, it's measured by an angle formed with a ray drawn from the center of the Earth, like center inside core, to the equator, and then the next angle, L, is drawn to that location, and that gives us our theta. Okay, that gives us our degree. So if I have the Earth over here in part B, Sioux Falls is located, if I start with a ray from the center of the Earth to the equator and mark it as L and create an angle, right? It's at 43 degrees and 33 minutes. And Dallas is at 32 degrees and 46 seconds. So what I want to do is I want to find the distance between Sioux Falls and Dallas. So I'm trying to find the length of this arc. Get it? Arc, right? We know how to find the length of an arc right there. And we need to assume that the radius of the Earth is 3,960 miles. So I already know our radius, go team, but I need to figure out the degree of the angle between these two cities and convert that to radians. So let's get started. I have 43 degrees and 33 minutes minus 32 degrees, 46 seconds. So if I take 43 degrees minus 32 degrees and 33 degrees minus 46 degrees, I've got 11 degrees plus a negative 13 minutes. Well, we can't have negative 13 minutes. It's important for us to remember that 1 degree is 60 minutes. So if I have 10 degrees plus 1 degree minus 13 minutes, I can rewrite that 1 degree as 60 minutes. So then I'd have 10 degrees and 47 minutes. Well, now I need to convert this into 100% degrees so that I can convert it to radians, because we don't have a methodology to convert from minutes to radians at this time. Well, that's going to be 10 degrees times plus 47 times 1 over 60, right? Because 1 second is 1/60th of a, 1 minute is 1/60th of a degree. That would give me 10.7833 degrees, just about, right? We are having to round. If I multiply this by pi over 180, that's how I convert to radians, that's going to give me about 1.88 radians. This is my theta, this is my r. We're trying to find the arc length here, which is s equals r theta. So I have s equals 3,960 times 0.188. Remember, that's in miles. So my arc length becomes about 744 miles. So the distance between those two cities is 744 miles. And again, step-by-step explanation of what we did is worked out for you guys. Let's talk about the area of a sector. So the area A of a sector of a circle of radius r is formed by a central angle theta in radians. We really like radians now, such that A equals 1/2 r squared theta. So let's solve an example. We're going to find the area of a sector of a circle with radius 3 formed by an angle of 45 degrees. So we do need to convert this 45 degrees to radians. So I have 45 degrees equals 45 times pi over 180, which would give me 45 pi over 180 radians, which simplifies to pi over 4 radians. And eventually, after we do enough conversions for angles like 45 degrees and 90 degrees and 60 degrees, we're going to know right off the bat how many radians they are. So I have that our area, is 1/2 r squared times our degrees in radians. That gives me 1/2 times 9 times pi over 4, which gives me 9 pi over 8, which if I plug into my handy dandy calculator using 3.14 for 5, I get about, sorry, 3.14 for pi, not for 5. I get about 3.53 square meters. And that's our answer for the area. We need to talk about two different types of speed, linear speed and angular speed. So let's suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled, right, that's our arc length, in a time t on this circle, then our linear speed v is defined as s over t. So s is how far it's traveled in units, and t is our time. Angular speed, this is a lowercase omega, of an object is the angle theta measured in radians. So how many, instead of arc length it's traveled, how many angles it's traveled. And we want to divide that by time. So omega is our degree in radians over time. We can then rewrite v as rw because v equals s. And remember that s equals r theta, which equals r times theta over t, which I just defined to be omega. So v equals r omega. So let's go ahead and solve a problem using angular speed. So here's example 8. I'm not sure exactly who comes up with these examples. This does not look safe, but here we go. A child is spinning a rock. He's having a real like David and Goliath moment as the end of a 2-foot rope at a rate of 180 revolutions per minute. I feel like that's really fast. Remember that one revolution is 360 degrees. And I want to find the linear speed of the rock when it's released. Well, remember that v, our linear speed, is r omega, which is r theta over time. Okay, so we need to convert from revolutions per minute, because that's how many times it's gone around, to radians. So if I have 180 revolutions per minute, that's so fast. I feel like that's really fast. Times 2 pi radians per revolution, that's going to give me 360 pi radians per minute. Okay, I just found my omega, not W, omega. If I say W, forgive me, but it's an omega. It's like a fancy W, like a Walgreens W. Ooh. So I have V equals R omega. Well, R is 2 feet, right? That's the radius of our circle. It's the length of his rope. So I've got 2 feet times 360 pi radians per minute. That's going to give me 720 pi over, just 720 pi feet per minute. Well, if we multiply this by handy dandy 3.14, we get about 2,260 feet per minute. So this rock is traveling at 2,260 feet per minute. I feel like that's really dangerous. I don't know about you. That just feels really fast. That's fast, right? So here's the problem all solved in case you want to check your answers. And if you have any more questions on section 5.1, let me know.